Cool. So these are classical things, maybe in our little subfield, right? This idea of recovering and detecting, and that there's this detection recovery gap for some problems. And this is a sort of new problem we've called counting, right? So it's another testing problem. Cool. And so one way to sell this story is with the phase transition diagrams. Another way to sell the story is I think that there's some really nice combinatorics going on under the hood, both for sort of testing problems and recovery problems, which are so let's get started. So the planted dense matrix, so the model we'll be thinking about at the moment is planted dense submatrix, right? And so we're going to have additive Gaussian noise. And the idea is we just have some vertices which will be in our community, which are denoted with this sort of blue dot, and each is going to be independently in the community with some k on n probability. So we're expecting the community to be sort of approximately size k, right, at about n. And these ones, we give them a slightly raised mean. Okay. So the algorithmic questions you could ask, right, sort of to determine. So if you're given either a sample from this model or a sample from the model where you don't have a raised mean, you could determine which one. You could try and recover something, so perhaps try and get an estimator over a particular vertex, whether or not it's inside the community, and counting, which we'll talk about in a sec. So these are sort of the existing phase diagrams, and I haven't really cited your properties, right? So there's a lot of work went into these two diagrams, and yeah, so the idea here is you have some sort of null, right? So everything here is normal 0, 1. Here you've got a raised mean on a little bit of it, and here you've got recovery. And the really nice thing, right, is that these are not quite the same. So there's these regions where detection is easy and the recovery problem is impossible, and also where it's there's evidence of hardness. And there's two different types of evidence of hardness. There's some reduction type stuff, and there's also low degree hardness. So basically, we want something where the sum test would fail. So we want to, instead of having one planted community, we want to have m planted communities, such that the total sum is the same as in the one planted community case, right? And so if you think about how you would do that, right? So now we're going to have the vertex label. So we still want the total size is going to be approximately k, right? So and if you wanted equal size communities, right, that would mean that you would place each vertex into one of these sort of m color classes with probability k, like 1 on m times k on n. Yeah. Okay, and so you would get this. And so you notice that the sum is correct, right? So each of these things will give you 1 on m times this lambda k squared. Okay, so the sum is going to be the same as if we just have one planted community. And the idea is that we are really going to be interested. So we're going to say counting, say, is telling the difference between, so in the most basic case, just having one planted submatrix, or having this situation where we have m communities. And so we don't want the trivial thing to work. If they had the different sums that were like different by a constant factor, the trivial thing would work, and it would be easy in that whole green region where the sum test works, right? So this is why we've set it up this way. And so, yeah, and we get the same diagram, basically. So in the case where, say, we distinguish this on community N2, it's the same as the phase diagram for recovery. Which is maybe surprising, right? Like it was easier to detect communities, like to detect the presence of one thing, like show existence of communities. And now we're saying that, well, actually, it's not easier to just count them. You don't have to recover the communities, you just have to count. And so what's our formal statement? So to say it formally, so most of the work in this paper went into the low degree bounds, right? So showing that no low degree polynomial works. And so by low degree, this is this idea, right? This conjecture maybe in the thesis of Sam Hopkins, right? That we consider that if we have a low degree polynomial where low can be up to log n size, so it covers spectral stuff. If that works, then we consider we have a working algorithm. Anything higher we'd consider too slow, right? So, and by working, we mean that we want this difference in mean to overcome this fluctuations, right? So in this situation, so we've got two different problems. For example, it could be the situation where we just have, sorry, I've gone back to the graph case here because these are the dodgy slides, but yeah, so you could have either sort of no planted structure, or you could have this one, or you could have this k and one, for example, and you want that when you have your graph or your matrix structure sampled from one of these, then your polynomial is going to be high in one and low in the other, with a bigger gap in the difference in the square root of the variance, right? Okay, so this is what we mean. And so under this is where we prove hardness, right? So we have, so I'll state it in the simple case of counting 1 versus m first. So here we have reasonably tight results, right? So what we say is that there's an easy test. So the easy test in this case is we sum up the diagonal. So we made the sums of the whole thing match, but then the sum on the diagonal, the more communities you have, you're going to get like m lambda times this k versus having only lambda times k. Okay, so you have a degree 1 test. Whenever sort of that count is highly concentrated enough, right? And otherwise we can show hardness here. Counting, right? So the actual formal problem is you're given, you know that you'll be given one of two samples. One of them will have n communities, one will have one community, which is called the counting, right? And so it's a testing problem between those things. Yeah. So maybe to make it a little bit closer to counting, it actually all goes through if you actually have m communities for some different m. And so this all works if now then you need some stuff about either the max of the two numbers or the difference, but if those are the same order, then it might be. Here we're talking about the binary model, right? So here we have some more parameters. Okay, so so this should be an S, right? So now what we're interested in is so here you're going to reveal edges with probability q plus ms, and here it's just going to be everything is like an Erdős. So you sort of got this background Erdős-Renyi random graph with probability q, and then here you have some sort of higher probability, and you have to be careful. I guess this is not greater than 1, but this is a model in the binary case, and then we also know some things, but here the story is a little bit different. So here we don't have any diagonal entries, right? So we set, I guess I should say here that we set the diagonal, we say there's no self loops, right? So this is whenever u and v are separate vertices, we reveal the edge with these probabilities. And so when you do that, then you get the following, right? So if you take a signed triangle test, this is our test statistic that we use. Yeah, and you'll see, so here the dependence on m is not strong anymore, right? So it's still open what the correct dependence on these two m's are. So perhaps some sort of, yeah, there's that's still open. And we also have this extra condition here, which says that the expected degree in the planted structure is large, right? So this is the expected degree of expected planted degree of a vertex on the planted structure. We also want that to be large. And so the nice thing is, okay, so getting slightly above the dependence on m and d, but these are the right thresholds in terms of being the same as recovery. So here, the recovery in Alex and Slill's paper, they also needed this condition and some sort of condition. Okay, great. Yeah, so I want to talk about this reduction because I think it's really nice. So the idea is that basically our proof that it's hard to test between these two problems can give a new proof that recovery of a single block is hard, right? So why is this interesting? So normally, maybe, I mean, if detection and recovery had the same thresholds, then you could use whenever it's hard just between having one block and 0 blocks, right? If that was hard, whenever recovery was hard, then you could maybe use that in your reduction. But for us, that has to have different bounds, whereas this testing problem does have the same sort of structure as this, right? So then it makes sense actually for this to have a more complicated testing structure, testing problem. So it's harder to test basically. And then we can use it to prove hardness of this algorithm. So where we want to prove it, right, is where recovery is hard. So that's this line here. And so we're allowed to sort of assume this. This is where the algorithm would be useful. Okay, so the idea is we're going to be given one of these as input. So either the 1 or 2. So in this case, we can really restrict to this like 1 versus 2 case, right? Because we know this is hard in various regions, and what we want is a. So we have one of these, we don't know which. We can apply the algorithm. So we're imagining the algorithm recovers in this situation, right? So we know that if the input is sort of our H naught, then the algorithm returns the right thing. Okay, so we get this. The annoying thing is we have no guarantee about what happens in the situation where this is the input, right? So then the algorithm could return sort of anything, right? It could return any k by k block, perhaps an empty one. You sort of imagine maybe it would return the one with the planted structure. Anyway, so I've drawn a few options here. But we do have the guarantee here. It's going to return the right thing, and here it returns something else. Okay, and so now you've got this k by k block. You want to do some tests. And so one thing you can do is calculate just the sum of the block. Okay, so in the situation maybe you're expecting, so if there is just one block, then you get this sum, right? And otherwise, so we've normalized it, right? So the sum of the whole planted structure is the same. So if you don't pick up all the planted structure, you're going to get a lower sum, right? And this concentrates quite well. So anyway, here you can sort of imagine you're getting very close to these values. Yeah, so you can, if the sum is bigger than sort of what it's meant to be minus a little bit, then you must be in the situation that, so in H naught, you're in this situation for free. In H1, you now know that you're pretty close to this picking up the planted structure, right? You might have some sort of like epsilon. Cool, and then once you know that you're vaguely in the right area, then you can calculate the sum of the diagonal of the k by k block, and that's going to distinguish it for you, right? Because the diagonal in your original case is only going to be lambda k, whereas the diagonal, if you've picked up most of the planted structure in the 2 community case, is going to be like almost 2 lambda k. And so you can threshold on the sum of the diagonal. Oh yeah, and this is just saying, yeah, you did need to do both tests, right? Because sometimes you could, if the diagonal of say this, which is a subset of the 2 communities, if you give them one community out of 2, then you would have this sort of like the right sum of the diagonal, even though as if you're in this case. Nice. Okay, and so now I want to talk a little bit about maybe some of the proof techniques, because I think it's really nice. So you end up defining these things, right? And so these will eventually be random variables, which are to do with the probability model P and the probability model Q. But everything we need about them basically holds sort of a formal polynomial. So you can imagine that you've got a bunch of variables which are indexed by sets, another bunch of variables which are indexed by sets, and you can recursively define this, and so you get these sort of nice calculations, right? So if your probability spaces are exchangeable, then all you care about is sort of the structure of the graph. You don't care actually which edges are in the set, just sort of like how they relate to each other in a sort of a graph, which is similar to what Salil and Alex had. For Salil and Alex, they had things which turned out to be actually cumulants. So ours are not sort of obviously cumulants. We'll see, maybe sometimes they are, but so this is the non-recursive definition, and somehow it feels a little bit like cumulants, right? So if if you forget this first term, so usually in cumulants, right, you'd have the sum overall tau, which are partitions of your set, and -1 to the number of parts in tau -1, and then you get a tau -1 factorial, and then you take a product over the expectations over just sort of like your random variables, which are indexed by the part. And each of these properties we do actually use in the proof, right? So we use things like if you've got so you're sort of thinking about these things as graphs, right? So if the edge sets are disjoint and our formal A's are multiplicative over these and our B's are, then we get that these R's are multiplicative over these things. Okay, so you basically we get some more complicated R structure than you might hope. You would sort of hope you would get cumulants in some way, in which case then instead of being a multiplication, you just get 0 whenever you have disjoint sets. And we don't have that. We have the like next strongest thing, which is that it's multiplicative. So we sort of don't have to worry about disjoint graphs. If you have this and you don't necessarily know that these things are multiplicative, but if you assume they are, then you get that the actual, like the R's are multiplicative. You also get that if these things are, if you have a set of these things such that these A and B values are 0, then you get out that for some sort of like closed set, so the set of forests, for example, when you delete edges and stay a forest. So if that's true, then you get that these R's are 0 there. Yeah, okay. And so maybe we should say how actually they relate to the set. So this is the formal definition, right? So here I get this. We care about this situation precisely, right? So it's say additive Gaussian noise. This is the only way when these R alphas make sense. Okay, so we see this, and these R alphas are a function of the planted. Okay. Yeah, and so for any subset, we just we can index a set like this, right? Just the product of every edge in that set. Yeah, so often we only care about the graph structure of these things, right? We do care, so you don't just care about the size of the set, you sort of care how the entries are related in general, because these are eventually going to be the expectation over these things in the two different models being used, right? So you sort of care about the graph structure with this. Yeah, so then the A's and the B's are formally exactly this, right? So if you're, so I guess we're thinking mostly of the submatrix, not a graph, sorry, but you're given your graph, or you sample your matrix like this, and then it's a function of the planted bit, right? In both cases. Yeah. Okay, and so yeah, this is the two ways you'd sort of define it, either recursively, so here you have to unpack it, or non-recursively, it's maybe a little bit grosser, but it looks like this. So this is the story, and we have to bound the sum of the squares of these R alphas eventually. So one more property we use. So this gets back to your question about how we get the corollary of the binary case, and it's not just thresholding, but what we can say is that yeah, somehow what we care about is the planted structure. If we can the planted signal, sorry, if we can shift that by some constant, then these R's don't actually change. And that helps us work it out. Yeah, and so here I wanted to show another property, which is like, they're not quite cumulants, but they're nearly cumulants, right? So say you have some, there are sort of 3 different problems going on, and you can either have, so this planted structure or this planted structure, but you imagine they're independent, okay? This X hat and X tilde. And then if you define the planted structure, which is the sum of both of them, then the advantage you get, so these RGs being larger, sort of thinking is helping us tell apart the two models, and somehow it's a nice convolution of these the ones for the individual problems. Okay, so if these were cumulants, again, you just have a sum of RG of 1 and RG of limits, but they're not quite. We have this nice-ish property. But discuss a little bit how it relates to the thing that's going on with Alex and Sleel's paper, right? So advantage in core, this core, these are, the idea is that if these are large, you can tell the things apart, and if they're small, you can't, right? And in both cases, when you have additive Gaussian noise, these are, we have proofs that sort of follow, you turn the same handle, right? And you get that, so Alex and Sleel had this, and we have this, right? And then if you unpack the definition of what everything is, so maybe I've told you a lot about sort of ad infinitum, what these R alphas are, and they have some sort of nice-ish properties, but not very nice. What was really nice in Alex and Sleel's case is you got these cumulants, right? Except it's cumulants over maybe something sort of an interesting set, right? So here, if you're looking at this K alpha, it's the cumulant over which random variables. So the ones indexed by everything in alpha, but also the thing you're trying to estimate, right? So in that case, this was like the community membership of, say, vertex 1 was literally what the paper was about, right? So this is, okay, so and then it's this cumulant of these. And so to remind people what the definition of the cumulant is, that's this, right? Yeah, so maybe one thing that's nice in the special case. Okay, so let's say, all right, so when you're thinking about a recovery problem, let's say you're trying to, sort of the recovery distribution is this, right? Because we have to make it one of our distributions. And then, so formally, if you have some function x, which is just a function of the planted structure, and it has this property, right? Then these two things do reduce to being the same, okay? And so, because here it's sort of maybe a little bit hard to see, sorry from all that's going on, but here we get mostly the same terms, right? So we mostly, the two things are in terms of these expectations over Q of some X alpha. And so in Sleel's and Alex's paper, right, they have this, sometimes you also look at the set together with this X, right?
Well, that's the magic that lets them get union.
Yeah, exactly. So basically, so if this likelihood ratio, right, if it really exists, right, then our thing, although it's not a cumulant over these variables, it is when you add this as a random variable. So in our particular case, so it has to be that the ratio of those two things has to exist in the planted structure. For us, it wasn't actually true this time, right? But you can imagine sometimes it was. And then you're saying that it sort of makes sense, right? You're saying that the testing problem is estimating this ratio. So the open problem is, well, it was in Sleel and Alex's paper, but I think it's super nice. So we have this, okay, so just thinking about the low degree versus where that's possible or not, right? So here we have this, but somehow, and here we had this, right? But somehow this was kind of cheating, right? Because we did a sum test. So if you just make sure the sum matches, you get a little bit closer. And so you get this diagram actually, that it becomes, it's not easy, right, in all of this region, as when you sort of compare against a null, which has 0 mean, the slightly raised mean, means it's a little bit harder somewhere else. And I think, and they also have a version where they get second moments to be correct and push that line a little bit, but not all the way, right? So it'd be really nice to have some H0, which is not obviously community structures, right? So somehow we fooled things by, we couldn't tell this apart from some other bunch of communities, but if you design some different H0, which doesn't look like a bunch of communities, and it was still just as hard to tell apart from this one planted community, I think that would be really nice.